I want to come back to our definition of this MSR mass, and I want to treat it really as if we have I want to think about it like an RGE. We have this cutoff. Let's see if we can write down a renormalization equation for that mass. It has a cutoff. There should be some equation that tells us how to flow in that cutoff. Let's see what we can learn from that. This is end of the side. So we have a cutoff. And we already said that we can treat R as a variable that parameterizes the mass scheme. And so we can vary R in this MSR scheme just like we'd vary mu in the MS bar scheme. So if you like, what you're doing when you vary mu in the MS bar scheme is you're properly taking into account kind of what fluctuations you want to put into your mass in the ultraviolet. And here, it's related to this kind of physics that's going on in the deep infrared that you're also being careful about. Okay, so we'll have instead of a mu RG, we'll have an RRG. The difference between the mu RG and the RRG is this time we're talking about powers. And we'll see what happens. So M pole didn't depend on R, so you get 0 for that. And if we just look at our scheme change formula, then we can figure out what the RG is. This delta M was a function of R, and we can define this as R, to get the dimensions right, times some kind of anomalous dimension that's just a function of alpha. So what this guy would look like is, again, just a series. Some perturbative series. RG writing out our equation. The equation we've come to is this. So R d by dr of the mass, because of the fact that we're dealing with a power, we get an R on the right-hand side of this equation. And that's really the only thing that's causing a difference from this kind of standard RGs that we've solved so far. And the fact that we got this power, which was 1, is exactly related to the fact that it was a u equals a half renormalon. If we looked at the renormalons that are further out, like u equals 1 would give r squared. But we haven't seen really enough to identify that, but that's true. So let's solve this guy in the usual way. Integrate on both sides. From what we just talked about, R is equal to lambda QCD e to the minus g of t. And we can also, therefore, write that d log r is, from this formula, dt minus g prime of t. If we follow that through as a change of variable, that's the change of variable we get. So let's switch variable from r to dt. So r, d log r is just the product of these things. And I can write it actually kind of a compact way if I write it as lambda QCD dt d by dt of e to the minus g of t. So we got a g prime, and then we got an e to the minus g of t. Let's just write that as a total derivative of that. So if I write it in terms of t, then that's the solution. That's the formal solution in terms of and I switch variable also in the anomalous dimension. And that's the formal solution to the RG. And this is a well-defined integral. There's no problems with doing it. The place where the integral could start causing problems is t equals 0, but we're never getting to t equals 0. We have cutoffs that are keeping us away from t equals 0. So it shouldn't surprise you that it's a well-defined integral, because we said that these things are supposed to be well-defined in masses that are not sensitive to these Renormalon problems. And taking the difference of two of them should again give us something that's not sensitive to Renormalon problems. But it's interesting that you see lambda QCD popping out. And that's because these two masses and the difference of these cutoffs is related to absorbing a different amount of these fluctuations, which were related to lambda QCD. So the evolution would just yield a new well-defined mass, M of R1, which absorbs a different amount of IR fluctuations. A shell out to R1 instead of just out to R0, if you like. Absorbing those fluctuations together with M pole to get something well defined, and how much you absorb is related to this cutoff. Okay? So we could do that integral at whatever order we decide. Let's just do it at leading log. So at leading log, we take this guy, and we just take the first term, some constant, alpha over 4 pi. And so gamma r of t, switching variables, becomes that constant over 2 beta naught if we keep all the factors. And then a 1 over t. Alpha becomes 1 over t. So if we're at leading log, we should think about having the leading log lambda QCD. So that's what the 0 means. There's this factor. And the integral we'd have to do would be this one, e to the minus t over t. So you see that t equals 0 is where there could be a problem, but away from t equals 0, there's no problem. do that integral, gives you an incomplete gamma function. That's just a way of saying that there's this special function that's defined to be that integral. Mathematica knows all about it. It's very useful. And actually, the incomplete gamma function is an example of a function that has an asymptotic expansion. So if we look at what happens if I expand this incomplete gamma function in alpha, t, remember, is 1 over alpha. I can expand about alpha. Then it has a series that has factorial growth. Just write that. So expanding about alpha equals 0 is expanding about t equals infinity. And the gamma function actually has an asymptotic expansion, and if you just work it out, plug it into Mathematica, say Taylor series, look at the terms, and you exactly see this, 2 to the n factorial, which is a u equals a half Renormalon. And so what's happening is when you take the difference of 2 of these gammas, you're converting this asymptotic series. If you take the difference of 2 of these asymptotic series, you're converting it into a convergent series. And we'll talk a little bit more about that next time, but I'll stop there. So we can see from this renormalization group, we can see again the renormalon, and we can see in what way it's sort of solved by thinking about making it shift from here to here, because it's the difference of these 2 gammas, not one of them individually. So we can use renormalization group techniques to think about these renormalon effects. And we'll talk a little bit more about that next time. The difference of these is convergent series. Yeah. Well, I'll write that down next time and show you it.